principle from a static equilibrium to dynamics by simply adding to your forces negative mass times acceleration. Okay? In particular, of course, we're going to extend this guy. The principle of virtual work, we have it previously that you cannot apply it in dynamics directly. It's just valid at equilibrium, static equilibrium. The summation of all the work, the virtual work is 0. Now, if I add to this applied load negative mass times acceleration, this exact equation will be applicable to dynamics, and from which you can derive all your equations of motion. Okay? Like I said, this is a deep principle that you can apply to anything. You have a beam, and the beam is just deflect under some load. And you know the solution for this problem under static equilibrium. If the beam is vibrating, just add to your static load, add to it negative mass times acceleration, and use the exact same equation. Okay? So use this as a principle. So see, we literally did nothing. We just got this guy from the left-hand side to the right-hand side, vice versa. But it has a very deep meaning, is that all the applied loads are in equilibrium with the inertial loads. So now any dynamics problem can be viewed as an equilibrium problem. Okay? Simply add to your loads negative mass times acceleration. Now you are in equilibrium. Okay? Any question about that? This is very important. Any question, please? If you accept this, like I said, immediately we're gonna extend our principle of virtual work. So principle of virtual work extended by D'Alembert's principle. We're going to write it as expected. Summation I equals 1 to n number of bodies F I applied on the body minus F inertial on the body, which is simply mass of the body, rigid body, or the particle times the acceleration dotted with dri equal to 0. And now we can apply it to dynamics. Okay? And let's see how this is going to be useful beyond Newton's equation. Like always, we're going to have a simple example solved by Newton and solved by this principle. Any question, please? Any question? Yeah, please, if you have any question, do never feel shy. Okay? Do never feel shy. Yes, answer.
Is this for a rigid body or is it for a specific?
Anything.
Okay.
Summation I equals 1 to n. This is number of bodies. It can be particles. It can be rigid bodies. Later on, we're gonna. Right now, I'm working for particles. Later on, we're gonna modify a little bit for rigid bodies, because I need to. Rigid bodies are experiencing not only forces but moments, right? Because they have rotational degrees of freedom. So we're gonna have additional term for the rotational motion. Yes, Jeff.
I guess if everything's at equilibrium and it's a dynamic problem, how does anything move?
Yeah, this is a good point. So now we're talking about two types of equilibria: static equilibria and dynamic equilibria. So this, you can call this as a dynamic equilibrium. Any question? Let's have this example. This example, I guess, 5.3 in the textbook, Chauvel-Jenkins. And then make sure the number. Yes, example 5.3 in Chauvel-Jenkins. This is a spring cord and a pendulum. We like pendulums. Theta, maybe this is some L naught here, and we're going to add displacement x. Okay? So this is M1 for the card, M2 for the pendulum. How many degrees of freedom do we have? 2. Anybody has a problem with that? X and theta? Okay. Okay. So let's have our origin here. This is I and J. Okay? So let's do it. R1, I'm in Newtonian mechanics, okay? So you try to turn the crank from Newtonian mechanics cautiously, though. So position, velocity, acceleration, and then apply the equations of motion. So R1 for the mass, starting from this origin, simply x in the I direction. This is easy to differentiate. It's x dot. I'll give you some time to write. So this is x double dot. Any question about that? This is easy to get. For the other mass, so R2 is x in the I direction, and then L cosine and L sine. If you want to do it in this frame, I and J, or it's up to you if you want to do it in the tangential and normal. I'm going to continue with I and J, so this is x plus L sine theta in the I minus L cosine theta in the J. Differentiate once, this is not bad. X dot L cosine, I plus L sine in the J. Differentiate twice, here is where it becomes a little bit tedious. So L cosine theta double dot minus L sine theta dot squared. Over there, it's the other way around. Sine theta dot dot plus cosine theta dot squared. Okay? We're done with accelerations. So we're going to apply equations of motion. Any question? We need forces. Let's have forces here. Within the framework of Newtonian mechanics, you have to isolate particles and bodies. This is the problem. So for this green guy, what are the acting forces? What are the acting forces?
Spring.
Spring force. So negative kx here. What else?
Normal force.
Normal force. Very good. What else?
Tension.
Tension. Yes. Okay.
Friction.
It's smoothness.
Smoothness.
Smooth. I'm sorry. Smooth. Frictionless. Theta. What else?
Gravity.
Gravity. So M1G. That's it. So summation forces in the x direction, equated with mass times acceleration in the x, and the same for the y. So this is easy to get. For the x, we have t sine theta minus kx equals m1 acceleration in the x direction. Here is r1 double dot. So the x direction part in the I direction is simply x double dot. The other equation is n minus m1g minus t cosine theta equals mass times the acceleration, the y is simply 0. These are the two equations. How many unknowns here? How many unknowns?
X and T. 3 and theta 4.
X double dot is unknown. The acceleration is always unknown, right? The second derivative of all your generalized coordinates. You told me in the beginning that we have 2 degrees.